Bienvenidos, Ushamdid, and welcome University of Maryland Global Campus learners from the CMIT-456 Section 6380 course for the Fall 2021 semester. This is the Cisco Networking Academy's CCNP ENARSI version 8 course curriculum, and in this packet tracer tutorial and activity, we're going to be taking a look at a very interesting topic, and that is packet tracer activity 19.2.1, where we're going to be configuring GRE, or Generic Routing Encapsulation. So let's go ahead and dive in and first take a look at the fact that GRE is actually something that was invented at Cisco and then was standardized. And here's one of the original drafts. I think it's 1701 here. And you can also find some information in RFC 1702, as well as, if I'm not mistaken, RFC 2784. And now I'm curious. So let's take a look at RFC 2784. And yes, here it is. RFC 2784 is on GRE. And again, these are always amazing reads because they give you a lot of the background information, help fill in the gaps as to why we have GRE and these technologies, and really what the thinking was behind their creation. All right, well, let's go ahead and dive into packet tracer activity 19.2.1. As you can see here, I have the topology up for our activity. And the first thing I want to point out is I'm using packet tracer version 8.0.1. And at the time of this recording, this was not the most current version of packet tracer. However, this is the one that I've been using for quite some time. I do need to upgrade, so I'll be doing that soon. So here is our activity. And again, this activity, we're sort of going to be walked through what to do. However, I'm going to throw a few little bells and whistles in here for things that you're probably going to want to consider and that you might actually be asked when you're doing the activity. So let's dive in and let's verify router connectivity. So it says ping router A from router B. Well, let's go ahead and give that a try. If I'm on router B here, and let's go ahead and work from user exec with the enable command into privilege exec mode. And again, we don't need to be in privilege exec to run the ping command. However, we are going to eventually need to be in global config, which means we would have to get into privilege exec. So let's go ahead and say ping. And I'm going to ping the publicly routable IPv4 address here. And you can see these are the outside addresses. These are the publicly routable non-RFC 1918 addresses that are being used for these two routers here on what we're going to pretend is the public internet. So router B's IP is 209.165.122, and let me go back and take a quick peek here. 122.2, and router A is going to be 64.103.211.2, and so that would be the IP address we would want to ping. So let's say 64.103.211.2, and so I have connectivity from router B to router A. No question that if I can ping one way, then I should be able to ping the other way, and just to prove that, let's make sure that we can do that. So I'm going to say ping 209.165.122.2, and as indicated earlier, we can ping between these two routers, so no problems there. Now, it wants us on router B to take a look at some of the interfaces that are configured here. Let's say show IP interface brief, and you can see there are only two IP addresses configured. We have our serial 000 interface configured, and that again is our internet connectivity. This is our publicly routable IPv4 address. And then we have the gigabit 00 interface, which is our inside LAN-facing interface coming off the back of the router here. Now, this big, thick blue pipe that you see here, this is not a physical connection. And I know sometimes learners, when they see this topology, they look at that thick blue line and they ask, well, is that a fiber connection of some kind? What kind of a connection is this? Well, that is just simply a logical representation of the GRE tunnel that we're going to be creating here shortly. So keep in mind, this is not a physical connection that's running north and south between these routers. Again, it is a logical representation of what is going to exist once we create the GRE tunnel. So from router B, ping the IP, and of course, we've pinged these addresses already. Attempt to ping the IP address of PCA from PCB. Now, remember, we don't have NAT set up here. If I was to say show IP NAT translations, you can see we've got nothing going on. What about show IP NAT? What does it support here? Statistics. There is no NAT set up here on router B. In fact, there's no NAT set up on router A. And so we're going to run into a problem here. If I say show IP NAT statistics, show IP NAT translations, you'll notice that these LAN segments are isolated from each other. Meaning, if this in fact was the true internet, we would not be able to natively take this RFC 1918.192 address space and use it to access the internet. It would get filtered out at the internet service provider because, again, these are private IP addresses. They're RFC 1918 addresses. They're not allowed to be routed on the internet. They're going to get filtered, dropped, however, blocked, whatever you want to say. And that's not going to work. And I think that's really what they're trying to show you here is, okay, let's pull PCA up. Let's pull up the command prompt. And can I ping the 192.168.2? Again, I'm trying to ping from PCA to PCB. And the IP address, let me double check here, should be .2. Yeah, .2. All right, so 2.2. Now, what's happening on PCA is PCA looks into its routing table and says, hey, I have no specific route to get to the 192.168.2.0/24 network, or to get to the /32 if you're thinking it's a /32, it has no way to get there. So what does it do? Well, the PC does what all PCs do when they're configured with a default gateway. It says, I don't have a route to get to that. However, I have a default gateway to which I can send this traffic and let the default gateway deal with it. Well, the default gateway just happens to be router A. So router A is going to receive this traffic and it's going to look in its routing table. Again, it's a router, right? So it's going to look into its routing table. And it's going to say, do I have a specific match for this 192.168.2 traffic? And it's going to say, no, I don't have a longer, more specific match. However, I have a default gateway, or a gateway of last resort is how we refer to it on the router. And so it's going to go ahead and shove that traffic out here to the internet. However, as I said, the internet is not going to route RFC 1918 traffic. And I'm sure what's going on here in this cloud and packet tracer is there's probably some static routing set up, and there's nothing that's going to get this traffic from the PCA LAN to the PCB LAN, just like it would in the real world. You would not be able to route that 192 traffic natively over the internet. And so here's the problem. This is the problem that GRE is going to solve from us. And you can think of it like this. PCA and this LAN segment, maybe this is in New York. And PCB and its LAN segment and its router, maybe this is in San Francisco, California. And so we need these offices to be able to communicate with each other. Now, you might be saying immediately, well, wait a second, I heard GRE is not secure, and you would be correct. There is no expectation of privacy when you're using GRE because there is no encryption involved. And this leads to the conversation of, well, then how would I protect that traffic? And I've provided you with additional links to some additional tutorials on how you would then integrate IPSec into this configuration to encrypt and protect that traffic. So for our purposes here in this video, we're really interested in simply establishing connectivity between, and again, I'm going to go with the scenario. We've got New York on the top, California on the bottom, and we need connectivity between these two sites. We're going to do it over the internet using generic routing encapsulation. So let's go ahead and dive in here. It says, what are the ping results? Explain. Well, I just kind of explained it. It's that RFC 1918 addresses cannot be routed over the public internet, and so this is not going to work. And there's no real routing information out here to get that traffic back and forth anyway. We're going to need the GRE tunnel. And so the rest of this activity, it kind of slowly walks you through it. So on router A, we're going to go ahead and we're going to set some things up here. We're going to get into global config. And the first thing we're going to set up is the tunnel interface. Now remember, the tunnel interface, and if I was to say TU, oops, sorry. If I was to do a question mark here, and actually what I want is interface, tunnel, and question mark. And I wanted to show you the range of values that you could use. So as you can see here, you can definitely create quite a few tunnel interfaces. However, typically, and again, this is typically what gets done is you'll start out with tunnel 0, or it'll be some number that has a special meaning to you that corresponds to the sites or whatever the case may be. However, here we're just going to simply go with interface tunnel 0. I could actually easily say, or more easily say int tu 0, right? And you can see right there, interface tunnel 0, change state to up. Now, a tunnel is a virtual interface. It's like a loopback interface. It's running in software. It really doesn't have a physical component on the router. However, we're going to sort of pretend that it does here shortly. But again, a tunnel interface is a virtual interface, not a physical interface. And if it's a virtual interface, just like a loopback address, we're going to give it an IP address. Now, again, we're going to use RFC 1918 addresses in the 10 dot space here and 255.252. So we're going to make it a /30. So the IP address is going to be 10.10.10.1. It's a /30. And now the tunnel interface has an IP. So if I was to say do show IP interface brief, I can check and see what is the IP address on my tunnel interface or tunnel interfaces if I had more than one. And there it is. Now, the thing I want you to notice here is the status and the protocol, right? So at layer 1, it's up because it's been created, right? And you saw that this is what happened right up here. Interface, tunnel 0, change state to up. However, the line protocol is down, meaning at layer 2, we're down. We don't have a connection into this tunnel interface. So think of it as like, you know, there is no end-to-end connectivity right now, and that's what the protocol is indicating here. So right now, tunnel 0 is up, down, and it's going to be this way until we bring the other side of the tunnel up. But let's go ahead and finish our configuration here. So again, we're tunneling out over the public internet. And so what is the interface that's facing the public internet out which I want to create this tunnel? Well, the tunnel source is going to be serial 000, and we already saw the information for this interface. It's also right here, and you can see right there it's the 64.103.211.2 IP address. Now, this is not changing the serial 000 interface IP. It's simply indicating that this is the interface out which, on this router, this tunnel interface will be trying to establish its connection to the tunnel destination. And again, the tunnel destination is simply the publicly routable IPv4 address on the other side. Now, could it be a loopback address on router A? On router B, it very may well be, right? Because we can have publicly routable addresses that we're using as loopback addresses on the router. And so that could be the case too. Here, it's the physical serial interface. And so we're simply going to say the tunnel destination over on router B is 209.165.122.2. So now on router A, I have a tunnel that's up. I have a tunnel with an IP address. It knows its source interface, in other words, the interface out which it's to go. And it also knows the destination of where it's trying to go to complete its connection, its end-to-end connectivity in that logical, I'm doing the air quotes here, in the logical sense. Now, this last command here in step D, this is one that always causes confusion among learners. And let me show you why. So just as I can say, do show IP interface brief, and we see that the tunnel is now up. And again, this may not be what you see on real Cisco routers because nothing is configured on the other side yet. However, Packet Tracer is kind of pretending that, hey, your interface is up, even though there's nothing for me to ping on the other side right now. So back to this conversation about step 1, substep D, where you say tunnel mode GRE IP. So just as I can see the information about the tunnel interface here, if I say do show run, and you could trim it down on a real router here, I'm not allowed to pull just the interface information, you can see that we have the configuration for interface tunnel 0 in the running config. And there's my tunnel source, there's my tunnel destination. Now that MTU command, which it's putting in here to take into account the overhead that GRE is going to introduce, which if the MTU max was 1500 would be 24 bytes. We also see the IP address here, but this is where the confusion comes in, is learners will see this command here and say, oh, okay, I need to say tunnel mode GRE IP, and they hit enter, and then they say, all right, well, let me look at my interface and let's make sure that my interface is correct. Where is the tunnel mode GRE IP in the running config? Why is it not there? And learners will feel that there's a mistake that's been made either in what they've entered in or that there's some sort of a bug in the software. And I'm here to tell you that this is not a bug, right? And this is not an undocumented feature. This is something I refer to often. 99% or 99.9% of the Cisco default settings, when you configure them, will not show up in the running config. So tunnel mode GRE IP is the default mode for GRE, meaning it's an IPv4 tunnel. And so that is why you don't see the GRE or the tunnel mode GRE IP show up. Again, on a real Cisco router, and let's see if we can get to a real Cisco router here. Whoops, sorry. See if we can get to a real Cisco router here. It should be router number 9. I'm hoping it's still up and operational, and there it is. And the same thing is true here, right? If I was to go into privilege exec from user exec and then get into global config and say interface tunnel 99 and then say IP address, 10.99.99.99, and we'll just make this /24 and then say tunnel source is going to be serial 000, and then I'll just throw a bogus tunnel destination in here of 209.165.122.2. We'll just make it the same as we're doing in our scenario. And there we have it. So if I say do show run interface tunnel 99, and again, I'm using a different tunnel number, you can see there is no tunnel mode GRE IP here. Well, what if I run that? What if I say tunnel mode GRE IP, and then we go back and we say do show run int tunnel 0 or tunnel 99? It's not there. And it's because it's the default, right? You'll also notice that if I was to say do show IP interface brief, that we should see, and I apologize, I should have trimmed that down a little bit. You'll see here that it is in fact Packet Tracer that's giving us this up-down or this up-up scenario that what you would typically see, because there's no connectivity to anything on the opposite side here, is that you would see up-down. Even after we've configured the tunnel source, the tunnel destination, the tunnel mode GRE IP, and the IP address, it would show up-down like you see here because nothing's configured on the other side. Right? And so again, I just wanted to run through that scenario real quickly to let you, make sure that you understand that this is something that you might see in Packet Tracer that you're not going to see in the real world. And more importantly, that command right there is not required. Right? Now we run it anyway because there could be some Packet Tracer points attached to that. However, it's not required. And the no shutdown as well, always a good, this is something I do all the time. On loopback interfaces, I type that when I configure them just out of habit, even though loopback interfaces are up until they have been shut down. All right, so we've completed router A's configuration. So let's go ahead and let's do a quick write mem and let's save the running config to the startup config. And let's come over to router B where we're going to do the same thing, except taking into consideration the fact that all of the values that we're going to be entering in for the remote side are going to be router A's values. So we go from user exec to privilege exec into global config. I'm simply going to say interface tunnel 0. We're going to put our IP address on here. Now remember, the IP address here, if it's a /30 and the .1 got used on router A, the only remaining usable IP in that /30 space is going to be the .2. And so then we're going to say 255, 255, 255, 252. And you can see that the state has changed to up. The tunnel source here, and actually let's do a quick check, do show IP interface brief, and it should be, yeah. So our tunnel source here is going to be serial 000, and our tunnel destination. Now remember, this is the publicly routable IP address that we're going to be seeing for router A, which is going to be that 64.103.211.2. Now you're going to see that it's going to say that the tunnel mode is up, and let's see, or the tunnel is up, but let's see if I say tunnel mode GRE IP, do we get points for this? So we're at 91% right now. Yeah, so it's not giving us any points for that, and I'm not surprised. Again, that is the default mode for GRE tunnels is IPv4. So again, this command, while not required, might not be such a bad thing to throw in here. Oops, sorry, let me say no shut, and we'll bring those interfaces up. So we've added this in here. However, we still have this issue. If I was to say do show IP interface brief, you can see that the tunnel interface shows up. Now let's test. Can I ping from one side of the tunnel over to the other? So do ping 10.10.10.1. Can I ping router A? Well, take a look at that. We have connectivity through the GRE tunnel. Can I ping 10.10.10.2? And I can't. So this logical connection here, this logical GRE tunnel between router A and router B, which is really going out over the internet, again, depending on which way we're going here, it's going out over the internet, is encapsulated, right? It's encapsulated. And so you've got a packet header, right? And it's going to be this sort of, think of it as the outer header that's going to provide you with the publicly routable information, right? Or the routing information that you're going to need for the public addresses. And that's sort of, and you could think of it as like, you know, your delivery header, GRE header information. And then you've got the packet payload. On the inside is where you find the private IP address information, right? So this information is going back and forth over the internet with the public, the source and destination that we configured, right? The tunnel source and tunnel destination IP address information. That's what gets it around the internet. And then once it arrives at the routers, that GRE or the destination header, the GRE header is, you know, then stripped off, looked at, and not in that order. It's looked at, then stripped off, and then it exposes the inner IP address information, which is going to be our RFC 1918 address information, if this, you know, for pinging between PCA and PCB or between the routers using the 10 dot addresses. And so that's what's happening, right? And so again, you can, if you think of it like this, you've got sort of this outer header, the destination header. I'll just put a D here. Then you've got your GRE header, and really the job of the GRE header is to tell the router what the protocol that is being used, and there's our tunnel mode GRE IP command coming into play, right? And this is where it's going to say, oh, is it IPv4? Is it IPv6? What is it, right? And so this is where we're going to say IPv4. And so then it knows it's an IPv4 packet. Remember, this is going to be all of your publicly, and I'll just put PR here, publicly routable, oops, sorry, did two R's, publicly routable information, right? The outer header, and then we've got the inner header, right? And this is really just the packet, the IP packet that we're trying to send back and forth. That's going to have all of our RFC 1918 information. And so this gets us through the internet, kind of tricking the internet into thinking, oh, we're using publicly routable IPs. It gets to the router, and that gets stripped off. The header gets looked at, and it says, oh, it's IPv4. That gets stripped off, and then we've got, it reveals the actual payload, right? The packet payload that has our RFC 1918 addresses. And that's really all that's happening with GRE. When you get into IPSec, it gets a little bit more complicated because we've got to start to talk about IKE v1 or IKE v2 and ISACAMP phase 1 and ISACAMP phase 2. However, that's a conversation for a later time. So I'm going to leave this here on the screen, and we're now going to discuss what's going on here with step number 3, because step 3 is asking you to configure a route for private IP traffic, because we still have this problem where if I was to try to ping from PCA to PCB, and let's pull this back up and let's rerun this again, and you can see it says pinging 192.168.2.2. Well, what's going to happen with that traffic? Because a lot of learners will think, oh, well, the tunnel is set up, so now it's going to work. However, the problem is that, again, PCA looks in its routing table and says, I have no idea how to get there to 192.168.2, wherever there is. I don't know how to get there, so what am I going to do? I'm going to send that traffic to my default gateway, which for PCA is going to be router A. Router A is going to receive that traffic, but have we made any changes to the routing table? No. The only changes are we have these directly connected new routes for the GRE tunnel, for tunnel 0. However, there is still no routing information on router A or router B for traffic that's being received, telling it what to do with that traffic for these internal LAN networks. That's the problem. So even though the tunnel exists, we still have to inform the router that when you're receiving traffic for this 192.168 network, or, respectively router A and router B, whenever they're receiving traffic for a 192.168, what do they do with that traffic? Right now, what they're doing is they're doing what they're told to do, and that is use their the gateway of last resort, which is just flush it out the serial interfaces. However, we already know that's not going to work, which is why we've created this tunnel, which is why we now need to tell the routers to route that 192.168 traffic through the tunnel, because then it would be encapsulated with this destination outer header, the GRE header, tricking the internet into thinking that, yeah, this is totally kosher. We're going to send this traffic over the internet. It works. It gets to the router. We strip all that off, and it reveals those private RFC 1918 addresses. So here are the commands that would need to be run on both router A and router B. So let's see how this is going to work. So from privilege exec, we get back into global config. I simply say IP route, and remember, in English, how I kind of, the mnemonic to help you remember this is my route to get to the 192.168.2.0 network, which is a /24, so we'll put the wildcard mask in here, is to go to router B. 10.10.10.2, right? Or use tunnel 0. So that's the next hop IP, right? So my route to get to this 192.168.2 network is to simply go to router B, to whom I am now directly connected, or so it appears to the router that there is a direct connection here, even though we already know that that is a logical connection. There is nothing directly connected here. It simply thinks it's directly connected. And so that's the command that we enter in on router A. And again, we are still not going to have connectivity. However, we will see a different message. The request will no longer time out, because now the request is being routed through router A. But what we should see here is, I was thinking we were going to see the destination unreachable here, and maybe I'm confusing myself with something I'd seen earlier. Again, we get the request time. I thought we would get the destination unreachable, but we'll table that for right now. So again, it's still not going to work is the key point. And the reason for that is that we have no route back. And in fact, hold on one second here. Let's jump a ping command in here, 192.168.1.2, and we should still see request timed out, although I thought we would see, oh, I'm sorry, I apologize. We have a default route. So it's going to say request timeout. It's not going to say destination unreachable on either side at either point, because there is a route. Even down here, it's still routing it out the serial interface, so we do get request timeout. I apologize. So let's take a step back here. So we've got the static route on router A. Let's come down to router B, and let's do the exact same thing. So let's get out of the interface subconfig mode. Let's say IP route. So my route to get to the 192.168.1.0 network, which is a /24, is to simply send the traffic through my directly connected, air quotes there, my directly connected tunnel interface, next hop over to router A, 10.10.10.1. And I have a typo there, I apologize. Let's see, 255. And so there we go. So now when I try to ping from PCA to PCB, we've got connectivity, because now router A and router B both know how to route the traffic for this 192.168 series of networks. And when I ping here, there we go, connectivity is working. So now let's spice things up a bit. Let's remove those static routes. Because in a scenario like this, yes, you could put the static routes in there. However, what if we were using a dynamic routing protocol? And this is something I like to walk my learners through so that they understand that in most cases, a dynamic routing protocol is going to be how this gets done. And it's irrespective of whether we're using OSPF or EIGRP. So let's start out with OSPF, and then on top of which I can simply configure EIGRP, and with a lower administrative distance, that's what we should see working. So let's do both scenarios. Let's just go ahead and say router OSPF 1, and we'll go ahead and say router ID, and since it's router B, we'll just say 0.0.0.2. And then let's get our network statements in here. And I'll just go ahead and for right now, we can say passive interface default. We'll say no passive interface tunnel. You know what? I think it has a problem on packet tracer with the passive interface on tunnel 0. So we'll say no passive interface default. We'll leave the passive interface out of here for now. And let's just go ahead and say 10.10.10.0. And this is a 0003 because it's a /30. And then we'll put everything in area 0. And now I also, remember, in order to, so that network statement there is going to allow us to establish the OSPF adjacency between router A and router B using this GRE tunnel. Now, I still need to advertise my local network here, which is 192.168.2.0, area 0. And then on router A, we would do the same thing. So let's go ahead and say router OSPF 1, and I'll just put a router ID of 0001 in here because it's router A, the first router, and then let's drop two network statements in here, 10.10.10.0, 0003, area 0. And upon doing this, I should see within a few seconds here, and there it is, that through the GRE tunnel, we've established an OSPF adjacency in area 0 between router A and router B. And again, remember, this is all going over the internet back and forth. And so we still need to advertise. If I say do show IP route on router A, take a look. We've learned via OSPF the route to get to the 192.168.2.0. And we know that it's over tunnel 0. And what we're going to do here is left out the network statement because over on router B doesn't know how to get to the 192.168.1 because I haven't advertised it yet. So let's do that. So network 192.168.1.0000255 area 0. And now they do. So on PCA, if I was to ping over there to PCB, you can see that this is going to work. And let's come over here to PCB and let's confirm that this works. And you can see that it does. The final thing we want to look at here in terms of the ping or connectivity, end-to-end connectivity, is let's trace it, right? Let's go to 192.168.2.2 and let's see where it takes us. And you can see this is showing that, hey, I don't know, the PC doesn't have a route to get to the 192.168.2.2, so it sends the traffic to its default gateway, 192.168.1.1. And then where does that traffic go? Well, it goes out over the interface on which the network's being advertised, which is the tunnel interface. That's where it's learning from that advertisement, and OSPF, shortest path first, is going to put that in the routing table as being the path to get there. and then we reach our destination. And if you were to do this with EIGRP, it would be the same thing. So let's go ahead and say router EIGRP1, right? And then we would add in our network statements for the 10.10.10.0, and I'll throw in a subnet mask here. And then I could throw in a network statement for the 192.168.1.0.0.0.255. And then let's go over here onto router B and let's do the same thing. And let's go ahead and say router EIGRP1. And if you're wondering why I'm not removing the OSPF config, that's because this should work irrespective of that, because EIGRP has a lower administrative distance. Remember, OSPF is 110, EIGRP is 90. And then let's add in our 192.168. Where are we at here? .2.0.0.0.255. And let's now go ahead and say do show IP route. And you'll notice that the 192.168.1 that we're learning over that tunnel interface via EIGRP is no longer being learned via OSPF. And the reason for that is the administrative distance of 90. That is what's going to rule the day here. So final check. Can I trace route? Absolutely. Can I ping? Absolutely. Let's try the ping from router B just to make sure. And there it is. All right, well, this is going to wrap up Packet Tracer Activity 19.2.1, where we took a very in-depth look at generic routing encapsulation, how to configure it, some of the semantics around it, the default being tunnel mode GRE IP, and then we spiced things up a bit by configuring both OSPF and EIGRP to leverage GRE to form that adjacency, that routing adjacency between router A and router B over the tunnel interface. And that is how we were routing our traffic. All right, well, that wraps it up for this video. Thank you guys so much for watching. Please let me know if you have any questions. And as always, best of luck to you out there in the course. Thanks for watching.